Hello, everyone. Welcome to ITS 350. So today we're going to continue with our discussion of cryptography. As you remember, last week we started looking at asymmetric encryption. At this time, you have completed the secret key lab and the hash or integrity lab, right? And you should be working on the first PKI-A lab, which is the lab for, we discussed certificate authorities basically. Okay, so now we will be focusing on, just going into more depth of asymmetric encryption. Before I get started, are there any questions? Are there any questions?
Not at the moment.
All right, no questions. I do want to remind you that we are currently on week 5, and next week is week 6, which basically means that you have an exam coming up, right? So exam 1 is going to be next week. And so it's a comprehensive exam. It's going to include everything that we've covered in lectures and labs so far up until what we cover on Thursday, right? So just remember, next Tuesday is exam 1. We will use on that Tuesday, the whole period. I will give you, it'll be a type of a written exam, and you will have to, either the questions are going to be there and you have to kind of type on there, or I'll give you an exam, like a Word document, and then you'll have to write the answers in the Word document, and then so we'll see. Either one of those will be the.
And we'll be taking.
Go ahead.
Oh, I was going to ask, and we'll be taking this live during class on Thursday, right?
Yes, it'll be live. So you have to be here on next Tuesday from 4 to 5:40. Will be the duration of the exam. You will sit in, and the Dropbox or the link, or however I'm going to do this in Brightspace, is going to close at exactly 6 o'clock, and it will not open again. Okay. Right, so the exam again is going to be Tuesday, a week from today. So on week 6 on Tuesday will be the exam. Yes. That means that this week we're starting the topics RSA, the lab PKI-B will not be due a week from Thursday. Instead, I'm not going to give you an assignment this Thursday to let you focus on studying for the exam. And then, we'll just start the lab and we will continue with it the Thursday of week 6. Okay, so that's really just, kind of the plan for the week, just so you can plan it out. Just be aware again, the exam Tuesday, 1 week from today at 4 o'clock. Okay. Any other questions?
Are we going to do any form of review for the exam, or is it just look over everything that we've done?
There's no review. It's just going to be everything that we've done so far. If you have questions, you can, ask me if there's anything that you're stuck with, but it could be anything from the labs. It could be anything from the slides. It could be anything from the notes, pretty much anything that we've done, any of the topics that we have discussed.
Since we don't have a lab this week, are we going to do anything on Thursday?
We do have a lab. You just don't have a lab that's going to be due a week from Thursday.
Okay,
so we are actually going to start the PKI-B. I'm just not going to make it required a week from Thursday.
Okay.
I'm going to give you 2 weeks for it.
Okay.
It's longer anyway, so you need the time. So it works out really well that way. But we will, so today I'm just going to go over slides, cover more material, and then on Thursday I'll just start discussing PKIB and how that one works, and then go from there. Any other questions? So certainly if you have a question about anything, ask away. I mean, because I could ask anything on exam 1. Remember, we'll have 3 exams. Exam 1 is on week 6. Exam 2 is on week 12, and then the final exam. All of them are comprehensive. All right. All right, so let's get started then if there's no more questions. I started grading your secret key homework assignment, so I think I'm like halfway there. So hopefully by tomorrow, I will be done with that homework assignment. So maybe you can check to see if I graded it. So far, they look good, so that, pretty much everything is there. So as I said, if I haven't gotten to yours yet, I'll probably get to it, hopefully by tomorrow. And then you'll have that as well. Okay, so I talked about the announcements. Yeah, and so now we're going to start our discussion. So you should be seeing currently the slides, okay? And let's say cryptographic tools. So I've gone over this already last week. I'm pretty sure we covered that. And I'm pretty sure after that, we got to here. And I think actually this was the last thing that we looked at. And then we started talking about certificate authorities, right? But I don't think we went over this part of the slides. So I'm gonna go over that now. And it kind of covers a little bit of all of the ideas, because all of these ideas, as you know, they're primitives, cryptographic primitives, and you understand those, and then you build on top of those to build even more complex techniques. All right, so we went over this. As you know, this gave us both confidentiality and authentication. Okay, and so now we're going to move on to the next. All right, so just go over a few things. So public key encryption structure. So a little bit about the history as we are actually moving into RSA. And RSA is the classic algorithm for asymmetric encryption. So we're going to take a look at that one. We're not going to do mathematical proofs of the algorithm or anything even close to that. We're mainly, as I said, usually with these things, our goal is to understand the algorithm. So we're going to look at the code and understand a little bit of how it works, the pseudocode, and some of the tricks that are used on here, like using mod and things like that, which are fairly common programming techniques anyway that you have to use every now and then. So public key cryptography, right? So the idea of having a public and a private key, right? So you want to have a public and a private key. So this idea was publicly proposed by Diffie-Hellman in the 70s, 1976, based on mathematical functions. The idea of asymmetric encryption, as you might imagine, a lot of people were already doing research about it, and they had probably shown in their research that this could work for the problem that we have, that chicken and egg problem, right? So how do we exchange the symmetric key? And so they came up with the idea, use 2 separate keys, public and private key, and the public key is made public for others to use, right? So we've discussed that. We needed some form of protocol is needed for distribution. So that was kind of the motivation there. So when it's directed towards providing confidentiality, public key encryption, as you know, you have a plain text message. We have Bob over here. Bob wants to send the key, so Bob is going to use Alice's public key, right? Then Bob sends the cipher, right, sends the cipher via the insecure channel. Alice, on the other end, is going to receive the message. She's going to use Alice's private key and obtain the plain text message. Okay, so that's a very important, as you know, that's something that you need to understand really well. Okay, so the plain text is just a terminology, is the readable message or data that is fed into the algorithm as input. Now, I should stress that you don't usually use RSA or asymmetric encryption to encrypt long messages, all right, because it's not very efficient, as we will see in PKIB. So one of the goals of PKIB this week is to look at performance. And you will convince yourself that actually, yeah, asymmetric is slower than symmetric, and therefore, as I said, I give you this example. You want to watch that game, right, the Super Bowl or something, and you're streaming the game. Well, you want to start the game now. You don't want to make your friends wait an hour for it to stream, right, and decrypt. And so performance is key to all of this. And so therefore, that's part of the models that we use. We need an encryption algorithm that performs the transformations on the plain text. That, the algorithm we're going to use in this class for this is going to be RSA. So we're going to take a look at that one. Public and private key, you have a pair of keys, one for encryption, one for decryption. And then we have the cipher text, which is now the scrambled message produced as output. And then the decryption key produces the original, I should say the decryption probably. The decryption produces the original plain text, okay? The decryption algorithm or technique. Now, if we want to focus on authentication, right, we take the plain text. So again, Bob is going to use Bob's private key. And the algorithm, you can see there, RSA is indicated. Then we have the transmitted ciphertext, which is sent over the insecure channel. Alice, on the other end, will use her RSA algorithm, right? She will take Bob's public key that she has, because Bob used his private key, and she's going to decrypt the message and obtain the plain text. Again, usually it would be just a symmetric key that's being sent over. The user encrypts data using his or her own private key. Anyone who knows the corresponding public key will be able to decrypt the message. So one thing I could do, let's imagine this scenario. We have our exam coming up on Tuesday, right? And I'm going to send you an email. I'm going to send you I'm going to send a message, using some general email. And you guys get the exam, right? And you get the exam. And you want to write that exam. But how would you, but let's say that you have a friend that's always playing tricks on you, right? So always trying to, do some prank on you. So how, and your friend also sends you a message with the exam, right? And your friend says, oh, this is the exam for 350, and I sent the exam for 350. How would you know, if you get the exam, which exam to do? Because remember, if you do the wrong exam, you'll get a 0, right? So you want to do the right exam. So what would you say? What would be the mechanism that should be used for you to know, okay, this is the right exam? What do you think? What do you think? Remember, we're going to have not just the written exam, but we're going to have a practical exam coming up as well. And in the practical exam, I like doing things like that. I may even, the actual exam itself, I could do that. So I usually just like to have like a hidden secret. I like to hide like a something. And then you have, you know, for you to get an A, you have to tell me what that was. But I could also do that. I could send you 2 exams just to make to add to the stress level, right? I could send you 2 exams and just say, well, you should only do 1, but how would you know which one to do? What would what would you be looking for that would give you some confidence that that's the right one to do? What do you think?
We utilize the hash of each file to figure out which
Sure,
one's
you
been
can use the
modified.
hash of the file, but that's not enough, right? Because the 2 exams are actually different. I've intentionally created 1 exam with 1 set of questions and another exam with another set of questions. They're all perfectly valid, but I will only grade 1 type of exam. So if you calculate the integrity, that's good, but what else do you need? And you can tell me, okay, professor, that's fine, but you need to do this, please. So what would you say?
We need some type of signature.
Some type of a signature. So how would that work?
The person, well, I guess the good exam would have to have a signature that you know comes from the actual good exam.
Okay. So how does that work? Now tell me in terms of public key cryptography, for instance, how would that work?
So you could, you as the teacher could become your own certificate authority and then sign it that way.
All right, but how? Give me the mechanics. I may not become a certificate authority, but okay, let's say that I send to you guys the following. I send the 1 exam, another exam, the hash of each encrypted, and I send my public key. So what would you do then to authenticate the exam? If I calculated the hash of each, right, the hash of each exam, and then I encrypted those hashes with something, and then I also gave you my public key, which is public, right? So which one of those, how would you tell which one of those is the right one? And I told you I use SHA-2 from OpenSSL and Linux. SHA-256, you know, one of those. I just stated.
Could you use HVAC?
Well, I mean, I'm saying I'm using SHA-256. This is the algorithm. No key for that. What's missing? How would you? No, this is a serious question, right? You can only do 1 of the 2 exams. How would you have confidence that they're both not encrypted? I've also, you know, to torture you, I've actually sent the exams in plain text. So, and you can't do both. Even if you had all the time in the world, you would not be able to solve. You only have time to solve 1. Haven't I given you all the tools to figure it out? How would you do it? Do you need me to like draw it maybe? Is that what it is?
That might help. I've kind of lost track of where. So there's 2 exams sent that aren't encrypted.
I get it. All right. So let's do that. Let me add a slide here. Okay. Maybe. All right. So all I'm saying is, you know, the practical exam, I like to do, you know, combinations of things, right? And so I might just say, I send you, you know, I would put this on Brightspace is what I would do. One of the problems would be, or the main problem is, here's the exam A, here's exam B. By the way, they're not encrypted, so they're actually that, you know, only you guys that can log into Brightspace can look at them, so that's, you know, perfectly fine. They're in plain text, so this is plain, this is plain. However, I did provide the hash of each of A, hash of B. I did do that. I also gave you on that same place, I put, you know, let's call it the 350 public key. Okay. So I created a public key for 350, and I'm telling you, and I also specified I'm not doing certificate authority for this one. That would be, you know, even more complex. Just this is fine. 350 public key. All right. And I tell you, okay, I use, you know, one of the OpenSSL ones in your labs. I don't know, whichever one. SHA-1, let's say. And I also tell you that I use OpenSSL encryption. I can even give you the command, right? RSA. And I encrypted the hashes. So these are encrypted. These are encrypted, right? Obviously, if I'm giving you my public key for the exam, I'm implying something. So how would you know which exam to work on? Remember, you have at most like 5 minutes to do this because the real exam is these, right? The real exam is what's inside these. So you got to start doing it. But how would you know which one to do? Does it make more sense now?
It's definitely a clearer picture than trying to visualize it myself.
What would you do?
It might sound really dumb, but I'm just gonna throw it out there and give it a shot. Is only one of the hashes actually encrypted with your public key, with the 350 public key? And so if it actually decrypts with the 350 public key, then that means that it had to have been encrypted with the 350 private key, ensuring that that's the proper one.
So I encrypted both of these with a private key, right?
Okay.
Right. So you would get then, let's say now you decrypt both. So you only have one public key, right?
Right.
You only have one public key. So what you would do is you would probably decrypt both of these with the public, right? And then that's going to give you the original hash. So this gives you the hash because remember, what you have here is the cipher of the hash, what is called the signature. I've signed it. So another way of saying is I took those original hashes and I signed them with my private key or the 350 private key. But then I gave you the 350 public key. So what you're saying to me is that you would take OpenSSL, you know, asymmetric public-private key encryption, and you would now decrypt these with my public key, correct?
Yeah, that would be at least one of the steps.
Okay, and now you have these two hashes, so they're decrypted. Do you agree? You have A and B, they are decrypted, right?
Yeah.
Now what do? How do you now know just by, let's say if you just used OpenSSL public and private key decryption algorithm with the 350 public key and you applied it to this cipher of the hash and this cipher of the hash, and now you get this and now you get that, does that mean that now you know which exam to use?
Not quite, because
Okay. What else do you need to do then? What else would you do?
Wouldn't you need to tell us the hash of the good exam?
Say that again, sorry?
Wouldn't you need to tell us the hash of the good exam?
I have. Here they are.
But I mean, like, you'd have to tell us the hash of the exam that we should take, and then we could tell.
Oh, I told you the algorithm that I used to create those hashes.
So we'd have to verify the integrity of both.
How?
You take your exams and do like SHA-1 sum and convert it to like a .text.SHA-1 and then compare both to the exams hashes that you gave us.
Okay. So in other words, what you just said, in other words, I think you meant now I'm gonna, you said you use SHA-1, so I'm gonna apply SHA-1 to this one, and I'm gonna apply SHA-1 to that one, and I'm gonna get new hashes, right? You're gonna get another hash over here and a hash over here. Hash, hey, let's call it my hash and my hash B, right?
Correct.
Because, you know, that's the integrity of the file. And then what do you do?
Then you just compare them at that point to the correct hash, and whichever one is verified that that's the correct one, then that's the one we should take.
Okay. Yeah, exactly, right? So then you're going to take, you know, these hashes, and only one of these is, because only one decrypted correctly, right? Only one decrypted correctly. Does that make sense?
So only one of the exams was, or exam hashes was encrypted with SHA-1, not both
No,
of them.
they were both encrypted with SHA-1, but I only use my private key on one of them. On the other one, I may have used another private key. But you don't have that public key, right? So that is to say, I use my private key on only one.
So kind of what we did for Lab 2 when we sent it to our partners.
It's exactly the same thing. I didn't change it one bit. That's the whole point. That whole mechanism is what you're doing here. Does that make sense? I just put it, all I did is I changed the problem to something else, to something real that I might do on an exam. Is this clear, guys?
Yeah.
All right, so if you want, you know, I can restate it, you know, think in other words, maybe think of it this way. That's why I keep saying that doing these exercises with a friend is very helpful, because that's the best way to understand. So let's say that I'm gonna, you know, I take one exam, right? This is exam 1. And what am I gonna do? I'm going to apply SHA-1 to it, right? Exam 1, and I get a hash of exam 1, right? I get that hash. You know that integrity means that only that exam could have generated that hash. Then I take the 350 pub, or sorry, not pub, private, right? And I'm going to encrypt this SHA-1. And this is going to give me Cipher 1, right? And then what I'm going to send is I'm going to send this, and I'm going to send that, and I'm going to send the 350, which you already had. I had already given you this from before. And so now what you have to do is you have to use that to verify that it came from me. Now the exam itself is not encrypted because I wanna make it harder by giving you 2 plain text exams, so you can't just, you know, you have to know which one was correctly done. So this one will check out, right? You will, when you receive it on your end, you will receive Cipher 1, right? And what are you gonna do? Oops. You take 350 hub, right? And with Cipher 1, you're going to decrypt it and obtain hash, correct? And then now all you have to do is you take also the exam plain text, exam 1, apply, I'm going to tell you to use SHA-1. So you apply SHA-1. This gives you, guess what? Another hash. If these two are equal, that's the exam you should use. So you have an if statement that says, if this hash and that hash are equal, use this exam. If it's not equal, you do not use the exam. Make sense? Remember, both of the, that I can, what I'm saying is the mechanisms don't change. But what might change is the way that I structure these problems. Okay? Are there any questions? No? Are you guys still there? All right, so seems like there's no questions. All right, so let's continue then. So we talked a little bit about that before, right? We talked about some asymmetric for confidentiality and authentication. Now we're going to proceed just a little bit to look at a little bit more of the details. Applications of public key crypto systems. So as you can see there, RSA is not the only one. You know, there are other approaches, something called Diffie-Hellman, DSS, elliptic curves, and so on, right? So there's research all the time on making some of these algorithms more complex or even in creating new frameworks. They have different, we will only focus on RSA, more of the classic example, so we will focus on that. Notice that you can do digital signatures with RSA. You can distribute the symmetric key, which is the main goal. And there's encryption of secret keys as well, right? So it's very helpful for a lot of things. And the other ones, they might have limits. Elliptic curves here seems to have the same properties or capabilities as RSA. All right. So requirements for a public key crypto system. So what do you want? First of all, before you actually start to develop the algorithm, you know, people said, you know, these are the things that we need. And then, you know, people proposed several techniques. And then really RSA, which is an algorithm developed by 3 people, was really the one that won out. So they wanted an algorithm or a technique where it was computationally easy to create key pairs. The public and private keys should be very easy to create. It's computationally easy for sender knowing public key to encrypt messages, right? So it should be efficient. Computationally easy for receiver knowing private key to decrypt ciphertext. Computationally infeasible or not possible for opponent to determine private from public key. So that's not possible. Computationally infeasible for opponent to otherwise recover original message, right? So it should be a good cipher. Useful if either key can be used for each role. And that's an important one, right? So useful if either key, public or private key, can be used for each of the roles of encryption and decryption. Commutable, right? So it's commutable. And so RSA, as it turns out, met all of these characteristics. And so it became the selected algorithm. And then, as I've said, over decades, basically, a couple of decades, people have been trying to, more than a couple of decades, have been trying to break it, you know, and so on. So RSA actually stands for, you know, these are the authors, Rivas, Shamir, and Edelman, right? Developed around the 1970s. That original idea and that original framework remains to this day. It's the most widely accepted and implemented approach to public key encryption, all right? It's software, basically. I mean, it's literally just software, but you know, this is an example of where math and software have made a huge had a huge impact in the world, right? In the world, our entire digital world works because of this. Another one out there that we will not cover in this class. I have a question there. Will your exam have any programming on it? It will. It might have some. I'm not looking for exact syntax, but I'm looking for pseudocode. You know, make it as close to Python or something like that as possible. I might ask something about algorithms briefly there. I don't. You know, it's usually never going to be more than 10 to 20 lines of code at most. So what I'm looking for is your understanding of the steps and how it works and all of that. I could ask you, for instance, write the Python code for the XOR hashing algorithm that we discussed in class. So I'm looking for your understanding of the logic of that algorithm, not so much that it has to be perfect syntax, okay? So another approach, elliptic curve cryptography, ECC, security like RSA, but with smaller keys. As I said, we're not going to look at all the variations. We're only going to look at the most commonly used one, and to get an understanding of how these algorithms work behind the scenes. All right. So public key certificate. So we started to talk about certificates last week in your lab. So here's a nice little graph. So we have here, we have a certificate authority, a CA, right? And we have the key. So the key is, Bob is the customer who goes to the certificate authority, right? So the certificate authority says, okay, give me your ID, Bob's ID, maybe in the certificate authority database, VeriSign. I want Bob's information, so Bob must have some kind of a business, address, all that. And then also, obviously, we're going to generate a public key. So we generate a public key of some kind. Then we use some kind of a hashing function, right? Some kind of a hashing function, SHA-256, etc. And we take the contents of this, the certificate, and we hash it. So we generate a hash code of the unsigned certificate. Then once we have that, the certificate authority will use, encrypt hash code with CA's private key, all right, to form the signature. So now the private key of the certificate authority, so the CA's private, is used to encrypt the hash. And now we attach that hash, which is encrypted, and that is called the signed certificate. Okay, so we're sending the signed certificate. Then on the receiving end, Alice over here, she gets, the contents of this. So she gets all the CA information. She's got Bob's ID and also Bob's public key, which is what she needs. She's going to take all of that and hash it because she knows the hashing algorithm. And she obtains a hash value. Then she's going to take the certificate authority's public key, right? She's going to use the certificate authority's public key, and she's going to take this, decrypt it with that. You can see there the decryption algorithm with that, and she's going to obtain the original hash value, this one, right? So this one over here. Now she gets this, and all she has to do is compare. Are they equal? If they are equal, then it's a match. The public key was not modified by Zelda. Alice trusts the CA. So a very important thing is that both Bob and Alice trust this certificate authority. It is incorruptible. And that's, one of the key things in all of this is that the certificate authority should be highly trusted. Okay? Questions? So this is clear, I'm assuming then. Okay, great. Good. All right. Another thing to consider is we take the same primitives and now we're going to create yet another structure, this one is called the digital envelope. All right, they're all basically a game on the same ideas, right? So now you want to protect the message without needing to first arrange for sender and receiver to have the same secret key. So it's kind of a thing where you know what, I'm just going to send everything all at once to my friend. My friend knows everything about cryptography, so they'll know that, you know, how to decrypt this, right? So it's something like you can literally just drop it in the mail, right? You drop it in the mail, it arrives at your friend, and your friend can literally figure it out. So it equates to the same thing as a sealed envelope containing an unsigned letter, right? So let's think about the digital envelope here, the same ideas. So you have, you know, Bob, and Bob wants to send a message, right? You know, some secret about, you know, the company that they're starting or something like that. So Bob is going to use a symmetric key, like from the block cipher encryption. So Bob is going to use like from AES or you know, some other symmetric key algorithm, right? Uses the secret key to encrypt the message. So now Bob has the encrypted message, the cipher, but Alice over here doesn't have the key. So Bob wants to send the key along, and so then Bob will use the receiver's public key, right? So Alice has a public key, right? So then Bob uses her public key to encrypt the key itself, right? And then that provides an encrypted key. And then now Bob sends both the encrypted message and the encrypted symmetric key all together. Zelda gets both of these, she intercepts these along the way. There's Zelda. But she cannot open it because she's got the cipher. But to break the cipher, she needs the symmetric key. But the symmetric key is there, but it's also encrypted. But it was encrypted by Alice's public key. Therefore, it can only be decrypted by Alice's private key. And Zelda does not have the private key. Therefore, she can't do anything. When it arrives at Alice's doorstep, Alice takes both the cipher and the cipher of the key and the cipher of the message, right? That's here in the envelope. What she does is she's going to take the key, the encrypted symmetric key, which was encrypted with her public key. She's going to use a decrypting algorithm and her private key. So Alice is private, and that will decrypt to the symmetric key. And then after that, she knows that Bob used AES. So then she's going to take the encrypted message, the symmetric key, and decrypt into the original plain text message. Okay? So on the exam, I could also do this, right? I could take that approach. I mean, I can take different kinds of approaches, you know, for the different kinds of problems. Are there any questions? As you can see, this again is just the same principles, only applied in a slightly different way. Any questions? All right, good. So it seems like all of this is clear, and that's good. Let's keep going there. All right. Don't forget that we also have the ciphers that are very simple ciphers, like the substitution ciphers, right? So you have that problem that we did for lab 2, that was due, I guess, last Thursday, right? Where you had to figure out how to convert from A, B, C to 26, 25, 24, okay? So usually I have these slides in here just to kind of remind me to ask you, how did that go? Did you guys figure it out? Guys?
I figured it out.
Great. All right. Good. All right. Well, if you have any questions, I guess just contact me. Otherwise, this is usually where I kind of bring it up to see if there are any questions about it. All right. So if there's no questions with that, let's move on then to our next topic, which should be very interesting. It's going to be RSA. Okay. So now we are ready for the RSA algorithm itself. And I think you'll find this pretty fascinating how it works, okay? So what I like to do with this, RSA takes a couple of weeks probably. I usually take, what I do is I do it in several waves, if you will. So first I'm going to do like a very simple presentation of it. And then I just add a little bit more complexity and a little bit more complexity as we continue to advance in the topic. Okay. So, but we are going to start working on RSA, which means we're going to switch over to the, because I'm done with these slides. If you notice, I'm done with these. So I have another set of slides, but they usually come after I've gone over these with my notes. So I'm going to then switch over to the whiteboard. And you should be seeing the whiteboard right now. Okay. So last week I went over the certificate authority, PKI-A. So we've gone over all of that. All right, so now we get into the very fascinating RSA. RSA. You've already seen where the name RSA comes from. It's the authors, Rivas, Shamir, and Edelman. Okay. And for those of you that are following along in the book, certainly read through chapter 23, right? It's got a lot of information there about Diffie-Hellman, then RSA. I will mainly focus on RSA. I do think, what's in the book is really good with regards to the RSA algorithm. And then, of course, using OpenSSL, which is what we're going to do. So even though, and this is, this recommendation, I always want to stress, even though I'm going over the algorithms for all of these, I'm not recommending that you should use your own algorithms of RSA, because while the theory is correct, your implementation of them may be wrong. Okay, so I'll give you an example. So let's say that there was a rumor that, Microsoft, and I'm not saying they did this, but, Microsoft, who was a very famous operating system, used encryption for some things, some communication. So they implemented RSA, but it turns out that they made a deal with an intelligence agency that they would make the implementation incorrectly. So that is to say, the theory and the methodology is right, but the way that Microsoft implemented part of that algorithm in their code was slightly wrong. And by adding that error and telling intelligence agencies about it, what does that create for the intelligence agencies? If, let's say, 60% of the world uses that Microsoft product, what could happen? Anyone? what could happen is that the intelligence agency, even though they would not be able, as far as we know, be able to crack or break a correctly implemented RSA algorithm, because the implementation had an error in the implementation, they can exploit that error to basically, break RSA. You see that? So it's not that they literally broke the RSA algorithm, is that they broke the error in the implementation. So this has actually happened quite a few times in the past, especially like with Wi-Fi routers. In the past, it has happened that the Wi-Fi routers use some type of encryption, maybe symmetric, asymmetric, but something was done incorrectly. And because it was done incorrectly, people were just able to figure that out, and they broke the encryption, okay? So that can happen, and that's why I would stress that whenever you use encryption, you use the well-known tools like OpenSSL, which it is assumed that OpenSSL has been implemented correctly, and therefore should not have any vulnerabilities. Make sense? All right. So what I'm going to do is I'm going to start going over the algorithm, the basic ideas of it. All right. Eventually, I will get to even more details of it, of the algorithm. But as I said, I kind of started at a high level, just putting out the basic ideas, and then we're going to look at a series of Python examples. What I call like a simple or toy example, and then like a more realistic example, let's call it better example. But then after that, we're just going to switch to the Python PyCrypto library, which is also in your book. I'm sure you can find it there. Explain. And then finally also OpenSSL. So really, for most of the labs where you implement things for the practical exam, you will be using either PyCrypto or OpenSSL, okay? So usually either one will work just fine. It just depends on how you want to do things. All right, so now that we've kind of talked a little bit about that, let's go ahead and start looking at RSA. Okay, so we're going to start looking at RSA. The RSA algorithm. All right, so RSA is a cryptographic algorithm which was designed by Ron Rivas, A. Shamir, and Leonard Edelman. It's designed at MIT. The algorithm was developed around 1977, right? So around that time, they finally came up with the algorithm that they believe, that I'm sure it has been tweaked over the years, but the algorithm has been, a cornerstone of the digital universe. So RSA, as you know, the basic ideas are that it uses a public and a private key. Okay. So it uses public and private key. As you know, the public key is known to everyone, and the private key is generally kept by the user. Messages encrypted with the public key can only be decrypted with its private key. Right, so it's used widely used in many applications, as you know, because of its advantages, in particular for key sharing. All right, so now we are going to look at the algorithm itself, okay? So we're going to look at, you can think of it as the steps that you would follow just in RSA alone. Remember, this is not even OpenSSL, right? This is just, OpenSSL is made up of a whole bunch of different primitives, one of which is, RSA. So again, suppose we have Alice and Bob who want to exchange information over you know, an insecure channel. Alice wants to send, so Alice wants to send a message to Bob. Alice wants to send a message to Bob. That and he needs to be able to read it. So using RSA, Alice can encrypt her message or the key. It doesn't matter because we assume that once we've encrypted the key, we can exchange the message securely. So interchangeably, as I speak, sometimes I will just say exchange the message, you know, and I just mean the key, or I might mean a small message. It doesn't matter, but you know, the plain text of some kind. So what are the steps involved in RSA? So let's kind of stop there. You know, from a high level point of view, what should happen? And as I said, we're going to look at this in a lot of detail as we start looking at the algorithm. So the first thing is that you will randomly and independently randomly and independently select two large prime numbers, which we're going to call P and Q. Okay, so that's the first thing, such that P is not equal to Q. All right, so that's the very first step. So first of all, what are prime numbers? Who can give me a working definition of a prime number? So who can give me a definition of a prime number?
Numbers with only two factors.
Okay, like what?
Basically, it can be divided either by themselves or by one.
Exactly. So a prime number by definition is only numbers that can be divided by themselves or by one. 17, 3, 7, 5, exactly. Numbers like that, right? So they have to meet those conditions, right? So if you have never played with prime numbers, I recommend you do that. Try to do some coding exercises on generating prime numbers. Should be a very fun exercise for you guys to do. Write the code that generates prime numbers, right? There's 11 one of them, 13, 17, and ... right? So they continue, and there's many of them. All right, so that's the first thing. RSA is built on top of this idea. Other people have tried to modify RSA to find prime numbers from other places. So for instance, they might generate from some data a sphere. Imagine this is a sphere. It's a sphere, and then it's built from some underlying data set, and then they look for like seed values in this, and then they use those seed values to generate P and Q and so on. Right, so there's a lot of techniques out there in research, but pretty much in our approach that we are discussing, we are going to look at just generating some prime numbers, right? That they need to be different, and they're going to be what we need to build this. So after creating detecting or selecting the prime numbers, you're going to calculate a value called n. So calculate n, which is the product, where n is really equal to P times Q. It's as simple as that. N is just the product of P and Q. what's important about this is getting P and Q, or sorry, getting N from P and Q is trivial. Whereas if you have N, you cannot figure out P and Q. Okay, so this is hard. But this is easy. Okay? So that's an important one there. You know, an important assumption is that it should be easy to compute N from P and Q. It should be really hard, or rather impossible, to figure out P and Q given N. Okay? So that's step 2. Step 3 is going to be calculate another value. Let's call it phi. Phi, right? So calculate another value, call it phi. All right, calculate a function or a value phi, which in where phi is as follows. So it's going to be P minus 1, you know, our previous P and Q, times Q minus 1. All right, so that, you know, you can see there, here's, you know, kind of a methodology of what we're doing. Number 4, now it gets a little bit harder. So far it's been pretty straightforward. You're going to now select an integer. Select an integer. Call it E. All right, so we're going to select an integer E such that such that let's do it down here instead. 1 such that E is greater than 1 but less than phi. All right, so it has to meet that property, and for now all I'm going to say is and other constraints. We'll come back to those other constraints because if I just say it right now, it won't make sense. And so I rather just say and other constraints, and then we will come back and look at those other constraints. Right, so it's an idea of it being co-prime, but we will come back to that later. This E is sometimes called the encryption exponent. And in fact, it'll make up the public key. All right, so it'll be part of what it, you know, what is going to become the public key. Then number 5, with number 5, you're going to now calculate D. Yeah, calculate D where you have this condition, okay? D, the previous, this one, E, the previous exponent, mod, which is a standard operation in all programming languages, right? Mod operation, phi is equal to 1. And this is the equal sign, not congruency or anything like that, but the actual equal sign. So it should meet that condition, okay? Where this is a 1 right here, this is 1, number 1. Okay. This D value here is sometimes called the decryption, or you can call it if you want to, the decryption exponent, and you'll see why in a second. All right, so we have that there as well. Now, given all the previous parameters, given, you know, P, Q, N, right, phi, E, and D, we can now derive the public and the private key, right? So given all of those, we can actually derive our key and our public key, right? So we can go over to the next page and we can say the public key is going to be the combination of N comma E. Okay, so those two parameters are provided in the encryption for us as the public key. The private key is going to be N comma D, as you might imagine. All right, so that's basically it. Now with those operations, you know, we have an algorithm for RSA that allows us to define the public and the private key. All right, so now that we have our public and our private key, let's go ahead and try to define how do we encrypt and decrypt. So we again, you know, we have this idea where Alice wants to communicate with Bob and transmit, you know, some message. Bob wants to communicate with Alice. He wants to send her a message M. All right, so we have the plain text M. Okay. The plain text message M. As you know, Bob already knows the public key of Alice, right? That's what she knows, and she wants to send her a message. So Bob knows Alice's public key. All right, so the question is now, how do we obtain the cipher given all this information? Well, what information do we have? So Bob has the plain text message M. Bob knows Alice's public key because we just established that it is N E, like that. All right, and so Bob then will use an encryption function, an encryption equation, which is like this: C is equal to M to the exponent E mod, which is the modulus operation, N. All right, where this N comes from there, this E comes from there, this message comes from there, and this is the modulus operation. All right. So now that we have our equation established, we're going to conclude, well, M is the plain text message. C is the cipher. Therefore, this is the encryption version of the algorithm, right? So we can encrypt with it. On the other end, if we want to decrypt, that means that we want to obtain the plain text message M. We can do C, right? Exponent D mod N. This is the decryption. So on the side of Alice, Alice has her private key. And her private key is made up of N comma D. Therefore, she knows that N and she knows D. So really D is the secret that she must keep secret because N is in the public key. She received the cipher, right? And then now she's able to decrypt and obtain the plain text message. Okay? And that's it. That's in a very simplistic way, in a very simplistic view, this is RSA, you know, in a nutshell, right? So now let's do a little bit of a simple example. We'll do several ones. As I said, your book has other examples as well. I strongly recommend that you read through those, okay? And then we're going to do a series of labs where we at a high level use OpenSSL, or we actually get into the code of SSL to look at a few more of the details. For instance, you know, things like additional, you know, I mentioned like additional constraints and so on. But right now we have a high level picture of how this works. Are there any questions so far?
Don't think so, not at the moment. Are we gonna have to actually? We're not actually gonna have to replicate this in code. Like, are we? Or
We are.
we are? Okay.
Yep. But I've provided some code examples already. And some of the, what I do is, some of the functions are there already. So for instance, functions like that mimic this part here, I've already provided the functions for you. And so what I like to do is I just like you to use the functions to figure things out. And I let you calculate P and Q, etc. We're going to use Python for this. So we'll see the examples of how that works in a very simplistic way. But you'll see that when we get to it. Also on the exam, I may just give you problems and yeah, so as I said, so focus more on the pseudocode of this, right? I'm not actually going to ask you to write this from scratch. I'm just going to ask you to kind of run the pseudocode and so that you can see the results in it. But, you know, the code is provided for you. You just have to kind of get it to run. All right, so now let's do an example of this, which we might do on you know, you might do a problem as well on this. All right, so let's do a simple RSA problem. All right, so let's assume that we want to encrypt the message. You know, the message could be, you know, something. This is a very simple example, by the way. We'll do other ones. This is just to illustrate the basic logic of it. We'll do a couple today, probably. I think we have time for like 2. We'll do 2 of these. All right, so let's do a very, very simple one. You know, we want to encrypt the message 7. Right, so we want to encrypt that message. So the first step, so what's the first step of the algorithm? If you're reading your notes, what was the first step of the algorithm?
Calculate 2 large prime numbers.
2 prime numbers, right? So how would you do that? You know, I will provide some kind of a function, right? So I'm either going to give you the prime numbers, or there's going to be a function in there, you know, calculate prime number. Usually these functions, you have to give it a seed value or the size that you want. But as you will see in the lab, you'll have those in there. All right, so choose two random prime numbers. So let's say that we did choose them and they are 5 and 3. Okay, so we do that. Then you're going to compute what? N, right? So what was the definition of N?
You multiply P and Q together.
P and Q, right? P and Q, very good. So that's going to give you 5 times 3, right? And that's 15, right? And that, just to illustrate. Then it says we're going to calculate phi, right? Phi. And for that one, we had said that it's P minus 1 times, Q minus 1, Q minus 1. All right, and that's going to be then 4 times 2. All right, so that gives you 8. So phi is 8. All right. Then after that, you have to select an E that is less than 1 and is less than phi. Right, so basically 1 less than E less than 8 in this case, and that it meets those constraints that we talked about. Now, those constraints that we were talking about is actually something called GCD. Right, the GCD. I'll explain the GCD in a second. But for now, just to kind of simple, because that will require us to do exercises just in GCD itself. But for now, let's just pick a value. Okay, so we would pick a value, and usually when you do this, I will give you the code. I mean, it requires some serious coding to do this part. So that function will be given to you. All right, so but GCD, basically, let's say we do that as a function, and it gives us the value 3. Okay, so now we've got 3 in there. And now we can move on to the next page, and we need to provide D, right? And so D, we had said, we wanted a value that met this condition. Again, for now, this would be a function that you'd have in your code, and the function will give you, let's say, 3 for now. So we're just keeping this pretty simple. We'll try to work this out a little bit more in the next problem. And so now you'd have public and private, which is made up of, what was N? 15, right? 15. So 15, 15. And notice here that D and E came out to be the same value. E is 3, D is 3. That's not correct, so I want to point that out, right, that these should be different because these are the D and E exponents, right, so they can't be the same. But for this example, just to illustrate that, they should not be the same because otherwise you basically end up with the same key. So now that you have the keys, then you proceed to perform the encryption. So given M7, right, we had said that the formula is C M to the E mod N, right? So that translates into 7, E was 3, mod, which is the modulus operation, right? And then what was N? 15, right? And so now we perform this operation. It would give us 343, right? We do mod 15, and that will give us a specific value. Now, mod in Python, for instance, is a percentage. And so it's the percentage symbols. You'll do some number, 343, percentage, 15, right, and so on. So this then gives us, let's say, 13, just some value. And now that's the cipher for 7. So now we want to proceed to decrypt it. So we want to do the reverse of that. All right, so now let's do decrypt. decrypt, and you're going to do M, right, which is what you want, the plain text message. C, D, mod, N. So again, now you have the C was 13. Decrypt here would be, the D exponent would be 3. Mod, which is the modulus operation, and then N was 15. And when you do this, it gives you a 7. All right, and then now you're able to basically encrypt and decrypt. So obviously this is a very oversimplified version of this. You will have a Python script in one of your labs where you will implement this, and just kind of it helps you to figure out, you know, the mod and little mechanics like that of the code. I will talk about those problems on Thursday, but like I said, you know, remember, I'm not usually looking for you to write any code from scratch. I'm literally just looking for you to understand the algorithms, the pseudocode of it, if you will. However, Python is so easy that you can, you know, given the functions that I've given you, you can pretty much get the results. Okay, you can get the results. For the more complicated parts, they're usually just functions in the code. However, we are gonna dig in a little bit deeper on this. So I do want to, you know, I do like to dig a little bit deeper on this one. Are there any questions so far before I continue?
So we are going to have practice with this in labs.
Yes, you're
Okay,
going
cool.
to have at least, so the way we do RSA is we do four things with RSA. We do, of course, the OpenSSL approach. The OpenSSL approach, right, that you've been using so far. We will also do PyCrypto. And PyCrypto just is a library. So it's pretty much like OpenSSL, but in Python. It's literally, so you don't really get into the math or the mechanics of this, okay? However, I do have at least 2 problems that I can remember of getting into like the operations. I call them, like SimpToy, I think. I have one, which is literally just implementing this problem or the next problem I'm going to do in Python, okay? And like I said, it's pretty straightforward. And then, so that, let's call that toy RSA. And then I have a more realistic RSA with the mechanics of RSA. But for that one, some parts you have to do it like this. Some parts you just have functions that are there to give you the value that you need. Make sense?
Yeah, as long as there's some practice to it, because it makes things a little bit easier once you're actually like hands-on with it. So
yeah, we are going to do a couple of more problems of these by hand, and then we are going to do in Python a little bit more. And the idea is, if you want to take it further, you can. By having the code, you have a starting point to look at all the other mechanics that I don't cover in the class, right? Because I'm not really going to get into all the details of RSA. I'm just kind of giving you a big picture of it. All right, so we have time for one more problem, I think. So let's do another one of the same type. Now this one is a more realistic way in which I can ask you to do this on the exam, okay? So on the exam, for instance, I could do something like this. I could say, I'd say RSA problem. And then I might say, compute the following. All right, so I'm going to say, given P equals 61 Notice the numbers are getting a little bit, obviously I can't use real numbers because, you know, you wouldn't be able to calculate things with big numbers. But I might say, given P 61 and Q equal 53, right? Answer the following. All right, so I might do that. Certainly have a calculator with at least mod for your exam. You might need it. All right, so let's say I might say answer the following. So I might say, okay, so what is phi, right? And I might say calculate n, right? I might give you those values. All right, so in the case of phi, you would say, okay, well, that's pretty straightforward. That's just p minus 1, q minus 1. All right, so that's going to be what? 60 times 52, and that is 3120. And there you go. You know, that's, you know, you answered it. N might be P times Q, right? And so you just say, well, P is 61, Q is 53. And again, you do the multiplication, 3, 2, 33. Make sense? So this is the approach. Then I might say, you know, given E, you have two options. So let's say I give you another, this is just simple ways that I might ask the questions for your understanding, right? So you have two options for E, right? So you have two options for E, 17 or 4,000. Based on the conditions of RSA, what is E? And explain how you came to that answer. So given what you've seen before, what would you say? Which one is E? 17 or 4,000? What's E? All you have to do is go back to the algorithm steps, correct? Go back. How do we select? What do we know about E so far?
That it needs to be greater than 1 but less than phi, and then there's other constraints that
Right.
have to
So-
dictate it.
Yeah, so I might say it meets the other constraints, and then therefore you just have to say, oh, okay, well, you know, it just has to be less than phi. So in this case, which one of these two is less than phi?
17.
17, right? 17. So your answer would be 17, and you just kind of say that. Right, as I said, we will get into those constraints, but that requires us to look at something called the GCD calculation. And so we will do that in a second. All right, so we will get to that in a sec. Or actually, we won't have time today, but we will get to it in the next time we meet. Certainly, I do recommend that you also read through the chapter. It would be very helpful if you feel a little bit nervous about some of this. Don't look at it as doing math per se. Look at it as code, right? So pseudocode programming. All right, so now we calculated E. So what's the next step? So far we have P, Q, we have N, we have phi, we have E. What else are we missing? Do we have everything that we need? What else are we missing?
don't we still need D?
We still need D, right? So we need D. So again, you can go back to the algorithm, and we said, this, right? So we said that for D, we can calculate it kind of by figuring this one out, right? Figuring this equation out. And so we can go back to that and state it. All right. So now we can say, all right, given DE mod phi equal 1. All right, so we have E is 17. So now we have D mod phi. Oh, phi we already have as well. Phi was 3120. All right, and that is equal to 1. Okay, so then we need to figure out D. So I'll show you. So usually these kinds of things you would solve again with code, with a function. All right, so what I usually like to do is, you know, I'll do that trick of try these 3 numbers and figure out the one that's the appropriate one or the best one, you know, something like that. So for instance, I might say on the exam, to make your life easier, you know, given D1, D2, D3, right? Tell me the one that should be D. Given that D1, I'm just going to do it for 1. So D is 2753. All right. So if D is 2753, that means that the equation becomes 2753 times, what was it? 17. Yeah, 17. And then mod phi, and phi was 3120, right? And then that should all be equal to 1. The remainder should be equal to 1. Okay? So then what you can do to prove this is you can take, well, first of all, 2753 times 17. Notice that the numbers initially were very small, but it's already getting pretty big, right? So 801. And you can work this out on your own, you know, convince yourself that that's what it is. So it's 46,801 mod 3120 equal 1. So that they should match, right? So both of these should match. And that just means the remainder should be equal to 1. So one way of doing it is you take 4681. Obviously, you can write code or do other tricks, but you know, this is just a standard paper and pencil approach, right? So you just take then, okay, 1, 3120, right? And that's going to be 1560. That's a 0. Okay, and then we have now the 1, you know, goes down here, right? So we got 15601. So now this is 5. 5 times 3120 is going to give you 15600, which means that's a 1. That's the remainder of the division. And guess what then? The mod operation of these will return that. Therefore, you end up with 1 equal 1, which means D is in fact an appropriate decryption exponent for the problem that we are trying to do. Does that make sense, guys?
Yeah, it's kind of just like filling in the variables.
Yeah, pretty much. I mean, you learn mod in any programming thing that you did, right? So whenever you want to print, let's say you only want to print every 100, right? So every 100, you use operations like mod to figure things out. So you do when I, let's say I mod, what is it, 100, right? Equals 0, right? So that's a common thing that you do. When you're programming, it just means that you're only going to print when your number is at 100 or you reach a 100, 100, 200, etc. All right, so anyway, so these are little tricks with mod that have nothing to do with encryption, but have a lot to do with programming. They're basic operations. So if you don't remember them, just kind of take a look at what has been done with that. And, you'll see it's pretty standard. All right, so anyway, the modulus operation. So now in the last 3 minutes that we have, let's just finish this out. So now we have all the exponents, and now all we have to do is the encryption and decryption. So for the encryption, encrypt, assuming we have, now I would say, okay, assume that your plain text message is 65. So what I want you to do is calculate the cipher, all right? And then so what you would do is you take, okay, well, I know the equation. Cipher is 65. 17 is E. So that's 17. Mod N, right? And N was 3233. So 3233. Again, you can do the computation over there, right? And that gives you, especially if you have a mod button in your calculator, that would really be helpful. You can also just use Google. I'm sure there's a calculator for that. So then this should give you, so 65 to the 17 mod 3233 should give you 2790. So certainly try to convince yourself at home, do the math and make sure it works for you. Then for the decryption, you're going to do the opposite, right? So now you want M. So you want M. So that means you need C, D, mod, N. So that's going to be then 2790. Notice this is a much bigger one. Notice how big this is becoming now, right? So the D exponent is, what was it? Who can tell me? $27.53, right? That's what we said over here. Mod N, what was N? 3233, right? So we do this calculation, and it should give us back 65, which is our original plain text message. Is this clear for everyone, guys?
Yeah, kind of.
Yeah, pretty easy, right? Pretty easy. One observation I want you to notice the difference in the size of E and the difference in the size of D. Do you see that E looks to be a lot smaller than D? You notice that?
Yeah, that's because you said that one way should be easy and one way, the other opposite way should be more
That's
difficult.
right. Remember, D is really the private key, right? D and N are the private key. The private key, as you will see, is always longer than the public key. And that makes sense because it's the one thing that you don't want anyone to break. So the longer it is, the harder it is for people to break. So it just works out perfectly that the algorithm for D gives you a longer, sequence of characters than for E. Okay? All right. So that is all the time that we have for today. I still need to discuss some of the things that I kind of just kind of didn't cover today all the problem, but we're just going to dig a little bit deeper on this one, okay? Just a little bit deeper on this one. All right, so just a little bit deeper on the details next time, and then on Thursday we are going to look at the PKI B lab, which basically means you'll be doing with OpenSSL some of these exercises like a digital signature, the performance, and then we will just kind of go over how to implement this in Python. So I'll show you, and then once I've shown you how to do it, you should be able to just do the exercises by changing a few numbers here and there, okay? But my goal is that you will see that by changing this parameter to that parameter, you'll be able to see some of the differences in the code. Make sense?
Yeah.
All right, great. So we'll stop here for today and just kind of remind me where we're going to be on, where we left off. I know we finished this problem, and so then I'll know where to pick up next time around. Okay? All right, so with that, we'll stop here for today, and I will see you guys on Thursday.
All right. See you Thursday.
Thursday.